All right, this is Southern West Virginia Community and Technical College course CH214. And I'm recording this lecture on my chapter 15. Your textbook in Brown will be some mixture of chapter 16 and 17.1 through section 17.3. I'm not sure how it goes. The lecture yesterday on 11 March covered acids and bases in general, some equilibrium problem solutions, and other characteristics of acids and bases, and how they change with certain types of composition. So you'll have to review chapter 14 video to get that information. We ended chapter 14 with a discussion of Lewis acids and Lewis bases. Now we want to get into chapter 15, which will eventually lead us to the concept and problem solutions for buffers. So what I want to do first is share the slides. Let's see. Okay. First, though, let me lock this meeting so it won't be interrupted. Okay. Now let's share the slides. There we go. And turn this into a slideshow. There. Now, let me see if I can make my screen a little bigger so I can actually see what I'm doing. Because I'm gonna be writing on this whiteboard, and I want to be sure it's coming through okay. So that should work. Okay, chapter 15. Chapter 15 in my textbook is labeled acid-base equilibria, but chapter 14 discussion led us into acid-base equilibria already. This is an extension of that, like I said, that will lead us to a discussion of buffers. So when you're trying to determine the pH of a solution, it's fairly simple. If you have a strong acid, for instance, then your dissociation for that acid in aqueous solution will be virtually complete. Okay, it'll be actually, for all intents and purposes, the dissociation will be completely over here. So if you know the concentration of acid when you mix the solution, you will know the hydrogen ion concentration, and then you can simply calculate the pH from Sorensen's equation. If you have a weak acid, then the reverse will come into play, and you have an equilibrium situation. So you'll have some of this and some of that, and you need to do the equilibrium solution for that problem, usually involving the ice table. But there's another fly in the ointment. Suppose instead of putting your acid into pure water, which would be the simplest scenario, the solution already has some things in it when you add the acid. In that case, we run into what's called the common ion effect. And if the solution has ions in it that are common to your acid, then there will be an impact of those ions already in solution on the pH, on the hydrogen ion concentration of your final solution. And in that case, we need to use Le Chatelier's principle. Okay, so let's see if we have some examples. Let's say we want to dissolve hydrocyanic acid in water, and it typically would give you this reaction where HCN reacts with water. HCN would be the acid. In this case, water would be the base, the Bronsted-Lowry base. That makes the hydronium ion the conjugate acid and the cyanide ion the conjugate base. Okay, what if we add sodium cyanide to this solution? Let's say in this scenario, we make up the acid and it's in pure water. And we already know how to calculate the pH from those conditions. But suppose we've prepared that solution and now we add sodium cyanide to the solution. Which way will the equilibrium shift? The question you have to ask yourself is there, are you adding an ion to the solution that's already there and part of the equilibrium expression? In this case, yes, you are. The cyanide ion, sodium cyanide, will completely dissociate. It will dissolve in water and add cyanide ions to the solution. If you add cyanide ions to this equilibrium here, what will happen? Le Chatelier says you've added cyanide to an equilibrium situation, and it will shift the equilibrium to the left. You've disturbed it by adding these cyanide ions. It will shift to the left, and what will that also do? It will consume hydronium ions. It will remove those hydrogen ions from solution and send them back into hydrocyanic acid. Okay, so what will that do to the pH? Well, it will decrease the amount of hydrogen ions in solution, which should increase the pH. Remember, the higher the pH, the more basic the solution. So if we remove hydrogen ions from solution, we are making the solution more basic. Okay, that's a common ion effect. So the common ion effect isn't good or bad, it just is. And we can take advantage of that common ion effect and produce a buffered solution. And when we speak of buffered solutions in terms of pH, we mean that the solution, once prepared, will resist a change in pH if we add an acid to it or a base, either one. The pH will not be constant, but it will resist a change, and it will be held within a narrow range by the addition of acid or base. If the solution is not buffered, for instance, if we form a solution from hydrochloric acid, and it produces this plus this, if we add chloride ions to this solution, what's going to happen? Nothing. This is a strong acid, which makes an extremely weak conjugate base. So if we add chloride, it's not going to do anything to these existing hydrogen ions. It won't pick any of them up because now it's a weak base. So the pH won't change at all. Say if we add sodium chloride to that solution. But if we add acid to the solution, then this addition of acid will increase the hydrogen ion concentration and decrease the pH significantly. Again, because that's a weak base. And if we add hydrogen ions to the solution, they will not combine with chloride ions to make HCl. Okay. So in that respect, this is not really an equilibrium situation. Okay, that's the case for strong acids. So when you make a buffered solution, you have to use a weak acid, which will actually establish an equilibrium. Okay, weak acid, strong base. So if you add hydrogen ions to this situation, then this, being a strong base, will accept those hydrogen ions and shift back to the left until equilibrium is reestablished. So that's what buffering of an acid will do in that situation. If you add a base to this situation, if you add hydroxyl ions, what will that do? Well, it's not going to combine with this. It's going to combine with hydrogen ions. Why? Water, in this case, is a very, very weak acid. It donates protons, yes, but very, very few of them, which makes the weak acid produce a strong conjugate base. That is a very strong conjugate base. So it will pick up those hydrogen ions and shift back this way. So adding a base will consume some of these. But once the equilibrium is reestablished, then we have a stable pH situation again. Okay, so that is rather a drawn out explanation of what a buffer does. It'll make a whole lot more sense when we try to solve problems. Okay. So when we solve buffer problems, typically what we do is we have a buffer established, and then if we want to see what the addition of any acid or base to it does to its final pH, then we look at the stoichiometry first. In other words, what kind of reaction is going to take place when you add the acid or the base. And then once you do that, then we look at it as an equilibrium problem. So it's actually two steps. Okay. And this is just an illustration of that fact. Step one is stoichiometry. Step two is equilibrium. So when I say stoichiometry, what I mean is when you add an acid or a base to a buffered solution, you treat it as if the reaction goes to completion, right? It goes, everything you add is consumed in the reaction. And then once you've established that situation, you treat that in your ice table as an equilibrium situation, and then it will shift back. And that will give you the final answer for pH calculation. And like I said, it'll make a whole lot more sense if we work a problem or two. Okay. Let's see. I'm going to skip these two slides. And now we're going to talk about the Henderson-Hazelbach equation, which is a very convenient way to determine the pH of a buffer that you've prepared. But it needs a little explanation. So we start off with this generic equation of a weak acid in equilibrium. So we add so much of the HA, it dissociates partially to produce some hydrogen ions and the conjugate base. Okay, so our expression for that, our equilibrium expression would put the products in the numerator and the reactants, the undissociated acid, in the denominator, and that's what the expression would look like. And remember, anytime you write a K, an acid dissociation constant, Ka, it has to involve only the loss of one proton at a time. You can't have, in other words, you won't have a power here on that one or that one, because you're only doing one at a time. Okay, if we solve this equation for the hydrogen ions, which makes sense, because if you're trying to determine the pH, that's what you need to know, the hydrogen ion concentration. So if we solve this one for the hydrogen ion concentration, we get the equilibrium concentration of hydrogen ions equals the acid dissociation constant times the ratio of acid to conjugate base. Okay. This was the first attempt. This was Henderson's approach, and that's where he stopped. In 1908, that's what he presented to the scientific community, this relationship. Then, just a year later, see, Henderson didn't, the concept of pH was not available at the time Henderson proposed this equation. Then a year later, Sorensen presented the pH system, the pH calculation, and Hazelbach took Henderson's work and applied the pH approach to that equation. Okay, he just did the log transformation for this first equation in the blue box. And when he did, he said, okay, we're going to take the negative log of the entire equation. Okay, and that's a mathematically valid process. Negative log of the hydrogen ion concentration, you recognize that as pH. The negative log of the Ka is the pK, the pKa. Okay, and then we leave the last part alone because it's a quotient of two unknowns. It would generate two separate p values. It would be pHa and pH minus, PA minus, and that wouldn't mean anything. So what Hazelbach did was he only generated the p's for the hydrogen ions and the k's. Okay, so we got this. pH equals pKa minus the log of acid divided by the conjugate base. But equations, at least Hazelbach, didn't like this negative in there. So he used another log rule, which says the negative log of this quotient is equal to the positive log of the inverse of that quotient. So that's the transition that's made from here to here. You just invert that relationship, and now the sign in front of the log becomes positive. And this is the Henderson-Hazelbach equation. If you know the pK for that weak acid, and you know the equilibrium concentration of HA, the undissociated acid, and the equilibrium concentration of the conjugate base, you can plug those values in and find the pH. And you don't necessarily have to go through the equilibrium calculations using ICE table. Sometimes you still do, but this is an extremely useful equation. And it, in fact, would be instructive for you as a student to learn how to derive this equation, because it has buried within it concepts of acid-base equilibrium and buffer solutions that become ingrained when you learn how to derive this equation yourself. Okay. Notice that for any given weak acid in a buffer situation, the only thing that's important to determine the pH of that buffer is the ratio of the conjugate base to the undissociated acid. So we could have a 1 here and a 1 here, or we could have a 0.5 here and a 0.5 here. It's the same ratio. So the ratio is important for determining the pH. And for any particular buffering system, you can have different concentrations of these conjugate base acids. As long as the ratio is the same, then it will generate the same pH. That's a very important point. Okay, so let's take this example. What's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? Okay, look at what you're dealing with here. You're given the K, 1.8 times 10 to the minus 5. Okay, so that K value is a constant. Okay, you're given the acetic acid concentration. So your equilibrium situation is acetic acid in equilibrium with hydrogen ions and acetate ions. And notice we're writing this in a simplified version. We're not using hydronium ions where acetic acid would react with water, which physically, that is exactly what happens. But for calculation purposes, this works just as well. Okay. So what do we know? What are we given? 0.45 molar acetic acid. Okay. But we're also creating this buffer with 0.85 molar sodium acetate. So what does sodium acetate do? In solution, sodium acetate completely dissociates into sodium ions and acetate ions. Okay, so by adding 0.45 molar sodium acetate to this mixture, we are actually adding 0.85 molar acetate ions. So you got this, and you got 0.85 molar acetate. Okay. Now, how does that help us with our calculations? It helps us with our calculations because we know this. pH equals pKa plus log of C2, let's see. Yes, okay. C2H3O2 minus divided by HC2H3O2 minus. Oops, not minus. There we go. We know this. This is our Henderson-Hazelbach equation. So to calculate the pH, we need pKa, right? That's the Ka. So we need pKa. We need to take the negative log of this, of that value, right? Negative log of that value. Let me just get my calculator and we'll do it right now. Find out what the pK is. 1.8 exponent minus 5. And we'll take the log of that right here and take the negative of that. 4.74. 4.74 is the pK for acetic acid. So that would go in here. Right there. And these would be 0.85 molar. And this one would be 0.45 molar. Okay. So now to find the pH, all we have to do is find that ratio, 0.85 divided by 0.45, and then take the log of it and add it to 4.75. The log is that ratio is 0.276. So I add that to, let's see, it's already in here, so I'll just add it like it is, plus 5.02. Okay, that's how we use the Henderson-Hazelbach equation. And there it is on the slide. Okay, we mixed this buffer ourselves. We made sure that by adding acetic acid, we produced this concentration of acetic acid, and then by adding sodium acetate, we generated a 0.85 molar concentration of sodium acetate. Okay, so for this buffer solution, let's take this for example. If we add hydrogen ions to this, that acetate is going to pick them up because weak acid, strong base. Strong conjugate base is going to pick up those hydrogen ions until we reestablish equilibrium. Now, will the pH stay right there? If we add a drop of acid, probably pretty close. But if we add 10 milliliters of concentrated hydrochloric acid, well, that's too much. Let's say 1 milliliter of 1 molar hydrochloric acid, it will probably only decrease that pH by a little bit, maybe 5.00 or 4.96, something like that. It won't change much because most of that added acid is picked up by that strong conjugate base. Okay, that's what happens here. In this case, where we add acid, then you go to the left and you decrease some of that and you increase a little bit of that, but the hydrogen ion concentration is doesn't move very much. It moves some, not much. If you add hydroxyls to this situation, what is it going to do? The hydroxyls in that case will be picked up by the hydrogen ions and make water. Okay. And in that case, what will happen? Well, when you add hydroxyls here and removes some of those hydrogen ions from this equilibrium situation, then Le Chatelier says it's going to shift to the right to replace some of those hydrogen ions. So that will stabilize the pH also. Only it won't put all of them back, which means that the pH will increase slightly. Okay? That's how a buffer works. Okay, this slide just says everything that I just told you right there. And this emphasizes the point that two things determine the pH of a buffered solution. One is the pKa of the weak acid, and the other is the ratio of conjugate base to undissociated acid. Those two factors determine the pH of the buffer. Now, we mentioned that if the ratio of these two facts, the conjugate base to the acid, are the same for any mixture, then the pH is going to be the same for that weak acid buffer mixture. But if you have only a small amount, say lesser concentration of these two, say this is 0.045 and this is 0.085, the ratio will be the same and the pH will be the same. But notice that, say, if we add acid, then it has to consume some of this conjugate base, right? It consumes some of it to reestablish equilibrium. Well, if we add a lot of the acid, eventually it's going to use all that up. And at that point, you don't have a buffer anymore. Because if you don't have the strong conjugate base, it cannot combine with the added hydrogen ions. That's known as buffer capacity. So the ratio is important as an intensity factor to determine the pH. But the amounts of these two determine how robust your buffer is, how much acid or how much base can be added and still maintain a pH close to that value. That's buffer capacity. And in general terms, we would call that an extensive property versus an intensive property. This determines the intensive property. The buffer capacity determines the extensive property. So in order to have large buffer capacity, you just need large values here in the correct ratio to give you the pH you want. This is an equation that quantifies buffer capacity, but it's there for illustrative purposes. We're not going to do any calculations with it. If you find yourself in a future employment where you need to take these factors into account, then you'll have that equation and you'll be able to use it. This beta, this capital beta, which is a Greek letter, stands for buffer capacity. And all it says is that with the change in number of moles of an acid or base, you get a certain change of pH. Well, actually, the N refers to normality. Let's see, acid bases. We haven't discussed normality, I don't think. During the first semester. Yeah, first semester we did talk about normality. Normality of an acid base. If your acid is monoprotic, like hydrochloric acid or nitric acid or acetic acid, then the molarity and the normality are equal, exactly the same. If you have a diprotic acid, then the normality will be twice the molarity, because for each mole of acid, you have access to 2 hydrogens. So any change in normality produces a change in pH. And the larger the number, the higher the buffer capacity. Let's see. So in this example, if we said 0.85 equivalents, which is a way of saying moles of acid, will generate a unit of pH change. And the larger the number, the better. Okay. So how do you choose a buffer, right? Because you can make buffers from any weak acid. What you want is choose the weak acid that will buffer at the right pH, because each weak acid has an ideal buffer range. Let's see, maybe I ought to draw a picture. Let me see if we're going to, I don't have my hard copy slides out. Maybe I ought to get those out. It's easier to follow along if I have my hard copies. I'll do that on my laptop sitting over here on the side. Then I can see what's coming. Let's see. Just take me a second. Okay. Chapter 15. There we go. Okay. Buffering capacity 15.3. Yes, we are going to, okay. So I won't draw a picture. I won't draw the plot here because we're going to get it in a subsequent slide. Okay, so when we're choosing a weak acid to make a buffer, you focus on the pK for that weak acid. And the pK should be as close as possible to the desired pH. And I'm going to prove it to you in just a minute. But the rule is you want the pK and the pH to be as close together as possible. That gives you an ideal buffer. Now, just as a point of interest, if we have this as our weak acid, it only has one pK because there's only one proton. But if we have this, remember, you get a pK for this reaction. Right? You get a pKa1, and then for this reaction, you get another pK. Okay? And these will occur at different pHs. Remember? This pK, this equilibrium will produce a certain amount of hydrogen ions. Right? It will be in equilibrium. It'll establish at a given K value. This one will have a much smaller K value, right? Because it's more difficult to remove that hydrogen from this anion than it is from a neutral compound. So that will give it a different pK. In fact, it'll give it a higher pK or more basic pK value. Okay. So if you have a polyprotic weak acid, then you have more than one possible ideal pHs. It just depends on which one you choose and where you establish the pH of your buffer as to which one of those reactions are going to be operative in buffering that solution. Okay, just keep that in the back of your mind when we go through the discussions here. Okay, so now we come to the practical application. If we have a solution of a weak acid and we start to add strong base to it, like sodium hydroxide is a good choice. So we have a solution of sodium hydroxide and a solution of weak acid. And we're measuring the pH constantly as we add base to it. So as you add base, the pH is naturally going to increase. And if you add enough base to the acid so that all of the hydroxyls from the base are now have now consumed all of the hydrogen ions from the acid, that's the equivalence point, or the stoichiometric point. So if we have some weak acid and we add a base, then at the point where these two amounts are equal, then you produce your salt. Remember, this is chemically speaking a salt plus water. Okay. So this one combines with that one, and when these two have all been used up, that's the equivalence point. Okay, this is what it looks like, that what we call a titration, an acid-base titration. And in fact, when we get back from spring break, we're gonna actually perform a titration in the lab and generate one of these curves for acetic acid, and use that information to calculate the K value for acetic acid. Okay, I'm going to show you how you do that in just a minute. First we're going to look at this titration curve. So in this case, say we have our example here is nitric acid and sodium hydroxide. Strong acid, strong base. Right? When you have a strong acid and a strong base, we learned from chapter 14 that when you combine equal amounts of a strong acid and a strong base, you get a neutral solution. Okay, and that pH, the pH at neutrality will be 7. Okay, and the titration curve will look like this. As you add base to the acid, then you gradually increase the pH as you're consuming hydrogens, and then the pH jumps up rapidly to that point, and it continues to increase as you add base until you reach this part of the curve. That's called a sigmoid curve. Okay, that's a strong acid, strong base. What happens with a weak acid and a strong base? Oh, well, okay. This slide says you can go backwards, right? You can start off with a base at high pH and add acid and go back the same direction, and the stoichiometric point is still 7. Right? So that's really a no-brainer. So if we look at this in terms of our problem solution, this titration can be divided into 2 sections. The stoichiometric problem says the reaction goes to completion, and we end up, for a strong acid, strong base, we end up at pH 7. But for a weak acid and a strong base, your stoichiometric problem then will reach equivalence at a different pH. But once you get to that pH, then you can work backwards as an equilibrium problem. Okay. So I thought they were going to show us, hold on a second. Let me go back right here. I'm going to look ahead. Okay. All right. We get the titration curve that I want to show you, but it happens way late in my slide set, and that was an oversight. So I will draw you one on the board. Okay, so here's our graph. This is added base. Doesn't matter what it is. Sodium hydroxide is fine. Added base in milliliters. Okay, this is the pH. And our acid, let's see, for argument's sake, is going to be acetic acid, a weak acid. So if we have just the acid in there, and we mark it off 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that's good enough for now. When we mix up a, say, a 10th molar acetic acid solution, what's the pH going to be? Well, the pH will be down in here somewhere, maybe around 2, 2.5, something like that. So this is our starting point. As we add base, what's going to happen? Well, as we add base, it's going to consume some of those hydrogen ions that have been dissociated, right? That's my abbreviation for acetate. So this is going to consume some of those. So that means the pH is going to start rising. Right? It'll go like this. Okay. At some point, you're going to, by consuming these hydrogen ions, you're producing acetate, strong base on this side. These hydroxyls are all used up, right, with the hydrogens. So now the strong base that you're generating is this acetate ion. So now you've got a balance between the acid and the conjugate base. So think back to the Henderson Hazelbach equation. Now you're generating, little by little, some more of this to ratio with that. Okay, so once you reach a certain amount of this and that, you're producing a buffer, because now you have some of this that can react to the addition of, in this scenario, can react to the addition of base. And you'll eventually get to a point where it'll go like that, and it'll flatten out like that. That's the buffer zone. And when you're getting close to using up all of this, now you don't have the equilibrium that you established before. And now it kicks up like that. Okay? And at some point in here, you reach equivalence where you've got an equal amount of sodium hydroxide and acetic acid, and they're neutralized. And that's your equivalence point. Right? So at this point, the moles of acid equals the moles of base. And by this, I mean the moles of hydrogen ions equals the moles of hydroxide ions. Okay? That's your equivalence point. And if this concentration is 0.1 molar and this concentration is 0.1 molar, then this also means that the volume of base is equal to the volume of acid. Okay? And that's usually the way we do it. It's simpler to calculate from that basis. Okay, so the volume of acid equals the volume of base in this case. Notice where the buffer zone is located. The middle of the buffer zone is 1/2 of the volume. right? You add exactly half of the volume toward equivalence, and you're in the middle of the buffer zone. It's not drawn very well, but that's where it is. So it goes up like that. So it's right in the middle is the buffer zone at this pH right here. Okay. So if you've added only half the volume of base, you have generated an equal amount of this. You've only neutralized half of that acid. So half of it is now over here. So in molar concentration terms, this concentration is equal to that concentration. So if we look at our Henderson-Hazelbach equation, pH equals pKa plus log of, I'm running out of room, so I'm going to do it like this. Now we've got equal amounts of this and that. Okay? Equal concentrations of conjugate base and acid. That's in the middle of the buffer zone. Where does that occur? It occurs at this pH right here. So if that is equal to that, right? Well, for our example, it would be this, 0.05 molar divided by 0.05 molar, half and half. This is equal to 1. What is the log of 1? Remember what logs mean. The log is the power of 10 that equals that number. So what power of 10 would equal 1? 0. Any number to the 0 power is 1. So this term goes out. And now we have pKa equals pH. So at this pH, that is equal to pKa. That's why you pick your weak acid with the pKa equal to, as close as possible, to the pH that you want to buffer. This relationship. So when we do our experiment, when we come back from spring break, we're going to do a titration with acetic acid. We're going to draw it out. We're going to find out what this pH is, and that will give us the pKa. And then we can calculate by log transformations what the Ka is. Okay? I just told you all about your experiment now. All right, and you can do this with any weak acid. Different weak acids will produce different pHs. And if you have, let's say you have a diprotic weak acid. Let me clean this out. Right here. Okay, if we have I think I need another marker. 1 second. I've got one handy. Well, brown will work. If this is added base, say we have a diprotic acid. The first hydrogen ion that comes off of that acid in dissociation will, let's start down here a little lower. It'll start to increase, and then you get a buffer region right here. And you go like this, and that equivalence is for that first proton. But then for the second proton, you get another buffer zone, and then it goes up for its equivalence. So this is the equivalence for the second proton. This is the equivalence for the first proton. This is the pKa2, and this is the pKa1. So with your diprotic weak acid, you get a buffer zone that could be made here, or you can make a buffer in that zone at a different pK. Okay? All right. So let's move on. here we have a problem where we're going to make a solution with 0.1 molar hydrocyanic acid, and its K value is given for us. And we're going to mix that with 0.04 molar sodium hydroxide. And both of them are in 1 liter. So we do that so that we can say, all right, it's 0.1 molar in hydrocyanic acid and 0.1 molar in sodium hydroxide and 0.04 molar in sodium hydroxide. All right, we're going to solve this the long way first. I don't like that brown. Let me get a, let me dig into my stash and get a fresh marker. There we go. Okay. So first of all, what are the major species when you mix this up? Well, it's a weak acid, right? So the major species for the acid are going to be hydrogen cyanide, right? The other major species for the, well, and water, of course, HCN and water. And then we've added sodium hydroxide. It completely dissociates. So the major species at the beginning are sodium ions and hydroxide ions, right? Those are the major species. Okay. Now, that's before reaction occurs. Sodium hydroxide is not a major species for the same reason it always has been. It completely dissociates. Hydrogen ions and cyanide ions are not major species because this is a weak acid. It doesn't produce many of them. So what are the possible reactions that can occur? Well, you've always got water, right? Like I said, in chapter 14, I mentioned this over and over again. This reaction between the amphoteric nature of water produces this reaction no matter what else is going on. It always happens. Okay, then you got your hydrocyanic acid dissociation, right? Then we can make up one where HCN plus OH minus produces CN minus in water, right? You're reacting the OH minus, or the strong base from the sodium hydroxide, with HCN. That's a valid possibility that could occur. Sodium and hydroxide, they're not going to return to sodium hydroxide. That one just goes out completely because it completely dissociates. It doesn't want to go back together no matter how hard you try. And then sodium's not going to react with water either. So these two go out. And now we're stuck with these first three to say which one dominates. Well, first of all, notice we have these two possibilities here, which are, well, actually three. They're all valid. But when we add the base to the acid, the first reaction that occurs is the stoichiometry between the base and the acid, this last equation, right? That's why we split this operation up into two processes. The stoichiometry comes first. So HCN and OH minus react to produce CN minus in water. And we let that reaction go to completion. Okay. So after this reaction, now we still have some HCN, right? Because we didn't use all of it up. We have some CN minus that's produced from that reaction. We have water, and we still have sodium ions. Now you can treat the reaction. Well, okay. This is one of those cases where it's just asking these hypotheticals. And then once you've asked the question, we're moving on. Right? So Store that away. We may need it again in a future slide. But now we're going to look at the pH of this solution made by mixing 0.2 molar acetic acid and 0.03 molar sodium hydroxide in 1 liter of solution. Okay, major species, obviously. Okay, these are the possibilities. These last two go out basically because they're stupid. They're not chemical. They will not occur. Let me put it that way. Okay, so if we look at these reactions in terms of their K values, the strong base, the OH minus, reacts with the strongest proton donor, right? And we can tell which one donates protons better, right? The first one with water or the second one with acetic acid? Well, the second one, right? The undissociated acetic acid donates protons more efficiently than water does. So that means the OH is going to react with the C2H3O2, the acetic acid, rather than reacting with the hydronium ions from water. It's going to pick up protons from acetic acid. Okay. In that case, this first reaction is our stoichiometry. We have OH minus reacting with H2CH, acetic acid, producing the acetate ion in water. We let this reaction go to completion. Initially, we have 0.2 molar acetic acid and 0.03 molar hydroxides. And we have none of the acetate ion. So we let it go to completion. That means all the hydroxides used up and only some of the acetic acid is used up. So actually that shouldn't say equilibrium. This should say stoichiometry or something like that, because this is not equilibrium. This is going to completion. Now what we have is 0.17 molar acetic acid left over in solution and 0.03 molar acetate ion in solution. Now we can go to equilibrium in our ice table. Well, this is presented as an ice table, but it's not really equilibrium, right? Otherwise, we would have a double barbed arrow up here. We only have a single barb, which means it goes to completion. All right. So now what reaction occurs? Now the reaction that occurs is the reestablishment of equilibrium based upon this reaction where the acetic acid dissociates into protons and acetate, the conjugate base. Our starting position, we're saying, is virtually no hydrogen ions, and we get these initial starting positions from the stoichiometry. Now, which way is the reaction going to go? It has to go to the right. It has to go toward producing hydroniums or hydrogen ions. So we're going to pick up some plus here and plus there because it's 1-to-1 ratio, and we're going to lose some of that in the process on this side with the acetic acid. And there's our expression at equilibrium. Okay. Now, if we generate an equilibrium expression for that equation, and we know what the K is because it was given to us in the initial problem, 1.8 times 10 to the minus 5 is the K. And this is the expression. We're saying that since this K is so small, that X in the denominator will go away. We can ignore it. And if we solve this for hydrogen ions, we find that that's the molar concentration and this is the pH, 3.99. Okay, that's how you would calculate based upon stoichiometry followed by equilibrium, the longhand version. But if we let the stoichiometry go, and then we know now that the concentration of acetate ions is this, the conjugate base is this, the acid is that. We can plug those numbers into our Henderson-Hazelbach equation and do the calculation and get the same value. So we don't have to go through the equilibrium setup. The Henderson-Hazelbach for an acid base, for a buffer solution calculation, will work just as well. And it's much simpler. But you do have to go through the stoichiometry first to find out what equilibrium looks like. Okay. So in this case, we've got another situation where we've got 100 milliliters solution of 0.1 molar acetic acid. What's the pH of this solution? Oh, okay. So in this case, we're dissociating the acid into hydrogen ions and conjugate base. And we set it up as an equilibrium. This solution would be 2.87. So remember that, well, remember the drawing that I did here, where you have pH here and base here. And I was trying to figure out where our starting point was. Well, this tells us exactly. If it's 0.1 molar acetic acid, our starting point is 2.87 pH. And then it goes up from there, like that. Okay? All right. So let me see. What do we have here? We're mixing 100 milliliters of 0.1 molar acetic acid and 50 milliliters of 0.1 molar sodium hydroxide. Okay, remember that equilibrium is based upon concentration. So if we mix these two solutions together, their initial concentration is going to change, right? 0.1 molar sodium hydroxide would produce how many moles of sodium hydroxide? Well, what's the total volume? Total volume is now going to be 150 milliliters. Or 0.150 liters. Okay. So how many moles of acetic acid are there? Well, remember, molarity is moles divided by volume. So moles would be equal to molarity times volume. Just rearrange the equation. So the moles of acetic acid, that's my abbreviation for acetic acid, is equal to molarity, which is 0.1 times volume, or 0.1 liters, right? 100 milliliters is 0.1 liters. So that would give us 0.1 times 0.1 is 0.01 moles. And now the concentration of acetic acid is equal to 0.01 moles divided by 0.15 liters. Okay. I think the slide is going to, let's see, let me go back. Yes. So the slide is not going to show you how this calculation is done. It's just going to give you the values. Right? So for the reaction goes to completion, you're going to start off with 0.0667 molar here. So 0.15 into 0.01 is 0.0667. And do the same thing for the base, and you get 0.0333 molar for the base. That's the starting position because you mix them together and you change the volume. So it looks like we're going to use up all the hydroxide and leave us with 0.034 molar acetic acid and 0.0333 molar acetate. Now all we have to do is plug those values into Henderson Hazelbach, right? This one goes in the numerator, that one goes in the denominator. The pKa is the negative log of the Ka that was given to us, and the pH is 4.73. Okay? Now, we've been talking about buffers up to this point in terms of weak acid and strong and conjugate base. But you can also make a buffer out of a weak base and its conjugate acid. And this is an example of just that. Calculate the pH of this solution made by mixing 100 milliliters of 0.1 molar ammonia with a Kb of 1.8 times 10 to the minus 5 and 50 milliliters of 0.1 molar ammonium chloride solution. Why did we pick that one? Well, let's take a look. All right. So when ammonia is put in water, what's going to happen? You're going to set up an equilibrium where you don't transfer one of these protons. You transfer one of those. So now water is the acid and ammonia is the base. So we're setting up a Kb situation here. So now you're going to have this one plus this one. Okay. And the Kb for that situation is 1.8 times 10 to the minus 5. So we'd say that concentration times that concentration divided by this concentration is equal to the Kb value. All right. So since we're adding these two solutions together, that explains why we're using ammonium chloride, because this is one side, this is the base, this is the conjugate acid. So if we add, if we're in a buffer situation and you add protons, you add hydrogen ions, an acid, then what's going to happen? Well, that acid is going to be picked up by that hydroxyl and shift the reaction this direction to replace them. If you add a base, the base is going to react with this species and pick up that proton and remove that, and then this is going to shift that way to replace this and make some more of these. No, that's not right. That won't give you a stable pH. No, that was wrong. No, forget that. If you add a base, this is a weak base, stronger acid. If we add a base, where's the hydroxyl going to get its proton? It won't take a proton from here. It has to take a proton. Okay, two choices. Where's that hydroxyl going to get a proton? It either gets it from here or here. It wouldn't make any sense to get it from here, because if it takes a proton from this, it just generates another hydroxyl. And that's a moot point, as they say. So it has to get it from here. So if we add hydroxyls, it picks up that proton and shifts to bounce this direction to replace that, which will also produce some more hydroxyls. So the pH will move, it just won't move very far. All right, so let's look at this example. Here's your reaction. And we're first going to look at it in terms of stoichiometry. Right? So we're starting off with this calculated concentration of ammonia, and then we're adding this much ammonium as in the form of ammonium chloride. And it's going to, oh no, I'm sorry, this is not a stoichiometry. This is equilibrium. Yeah, this is equilibrium. So when we, which way is it going to shift? Well, we start off with no hydroxyls at all, or virtually none. Probably should have put a squiggle in front of that. So the reaction is going to move to the right. And when it moves to the right, you're going to lose some ammonia and gain some ammonium and some hydroxyls. Okay. And now you end up with this in the expression, the KB expression here. And we're going to approximate that value and determine that X, the hydroxyls concentration, is about 10 to the minus fifth. And if we calculate the POH, which we would do first and then subtract it from 14, gives us the pH, then does that satisfy the 5% rule? Well, yeah, I do the calculation off camera, and it does satisfy the 5% rule. So we were correct in assuming that X is very small. So how would we use the Henderson-Hazelbach equation in this case? Right? Because Henderson-Hazelbach was written for weak acids, and this is a weak base buffer type. Well, let's see. If we start off with this arrangement like we did before, then we know that the KB is this one. The Ka would be this value, right? We know how to calculate Ka. So the Ka for the reaction where we put ammonium and react it with water to produce, remember, the KB would be ammonia plus water yields ammonium plus hydroxide. But the Ka expression takes the conjugate acid and reacts it with water to produce ammonia and hydronium ions. So we need a Ka expression. And the Ka expression then is 5.56 times 10 to the minus 10 for this reaction. Now we can use Henderson-Hazelbach. The pKa for that K is 9.25. Now that we know the Ka, we can use Henderson-Hazelbach. We just also need to know what are the values for the acid and the conjugate base. Okay, so the conjugate base for acids would be a negatively charged species. But for this reaction, the acid is the charged species of ammonium ion, and the conjugate base is the uncharged ammonia. And then we plug in those values, and we have the pKa for that reaction, and we get 9.56, which is what we got with the previous exercise. So using the Henderson-Hazelbach is a no-brainer for weak acids in buffers. But for weak bases in buffers, it's a flip of the coin. Either way would be equally as tedious. Okay. So let's say calculate the pH of a solution made by mixing 1 liter of 0.5 molar ammonia and which has a KB value of 1.8 times 10 to the minus 5 and 0.5 liters of 0.1 molar ammonium chloride solution first, then by adding 0.1 mole of HCl as a gas. We do it as a gas because that way it doesn't change the concentration of the other species. If we added HCl as a liquid, then we'd have to recalculate concentrations. All right, so in this case, the ammonia concentration we start with is 0.5 moles in our new volume, which would be 1.5 liters, right? 1 liter plus 0.5 liters. And the ammonium ion is 0.1 in that same volume. So now we can calculate, well, actually, what we're going to do is the stoichiometry first. And how do I know that we're doing that? Because we mixed these two different solutions. And we also added 0.1 mole of HCl. If we had not added 0.1 mole HCl, we could have taken these calculations and gone straight to equilibrium. But since we added the HCl, now we've got to do some stoichiometry first. So if we add 0.1 mole of HCl, notice what we're doing here. We're doing the stoichiometry in terms of mole, not concentration. All right, so I got a little ahead of myself. We don't calculate concentration until we get ready for equilibrium, because you can do stoichiometry with pure moles of reactants. We've done that before with other types of reactions. Okay, so we're starting with 0.5 moles of ammonia and 0.1 mole of ammonium and 0.1 mole of hydrogen ions added as HCl. All right, so that gives us before and after, right? We assume that all these hydrogen ions are consumed and produce 0.2 moles of ammonium ion and leave us with 0.4 mole of ammonia. Now we can calculate concentrations, right? So we got our stoichiometry done. Now we're going to set up concentrations to do our equilibrium. So now if we have this as our acid, this is our base, we can use Henderson Hazelbach because we've done the preliminaries already. Okay, we've done the calculation where we determined that the pKa for that reaction, and I just reproduced it here, is 9.25. Then the Henderson Hazelbach puts the conjugate base on top and the acid on the bottom, and we do our calculations and we find that the pH is 9.55. Okay. Calculate the pH of a solution at the equivalence point when 100 milliliters of 0.1 molar acetic acid is titrated with 0.1 molar sodium hydroxide solution. Okay, remember in chapter 14, we did a qualitative assessment of what kind of pH can you expect when you add, when you combine a weak acid and a strong base, or a strong acid and a weak base, and where can you expect the pH to show up? Well, with a weak acid and a strong base, our equivalence point should be basic. It should be greater than 7. That's the qualitative approach. This is the quantitative approach here. We're actually given amounts of acid and given amounts of base and said, at the equivalence point, and let's see, does that make sense? 100 milliliters of 0.1 molar acetic acid titrated with 0.1 molar sodium hydroxide, when does that equivalence point occur? Well, since they're equal concentrations, it occurs when you've added 100 milliliters of sodium hydroxide. Now you have equal moles of acid and base. That's the equivalence. Okay, that's why in green down here, the total volume at the equivalence point is 0.2 liters. 100 milliliters of acid plus 100 milliliters of base is 200 milliliters or 0.2 liters. So before the reaction occurs, the concentration of each would be 0.05 molar. All right. So initially, the concentration, when you add them together, you have to, this is a thought problem. When you add the acid and base together in sufficient amounts, then before the reaction occurs, right, you freeze frame. You have a concentration of acid of 0.05 molar and a concentration of base is 0.05 molar. And nothing on the product side. Now, at equivalence, you don't have any acid left, you don't have any base left, and now we've produced completely C2H3O2, the acetate ion. Okay, that's where we start with our equilibrium calculation. In this case now, since we only have acetate ion, it's going to react with water. There's nothing else for it to react with. That's it. So our reaction then is the conjugate base of acetic acid plus water yields acetic acid plus OH minus. So that is a KB situation there. So what we have before the reaction is 0.05 and none of these over here. And we're going to lose some acetate ion and produce some acetic acid, plus we're going to produce some hydroxyls. And after that reaction, we have this arrangement, 0.05 minus X, X, and X. Okay. Now, instead of using Henderson Hazelbach, we're going to use, since this is not an acid reaction, this is a base reaction. This is a KB. So we need to calculate the KB for acetic acid, which would be, the acetate would be the KB of 1.8 10 to the minus 5 divided into 1 times 10 to the minus 14 is 5.6 times 10 to the minus 10. And then we set up our equivalence of the K, right? And we're going to say that X is so small we can ignore it and find out what the pOH is, and then the pH is 14 minus that value. So 8.72 should be the equivalence point for acetic acid reacting with a strong base to equivalence. And this is pretty close to where it will occur, just under 9. Now you can do that type of calculation for any weak acid. You can find out what the equivalence point is. And this is what those curves would look like. So for acetic acid, where the Ka is in the neighborhood of 10 to the minus 8, the equivalence point is going to be up here in the neighborhood of 9 or 10, right in there. For weak acids that have, excuse me, hold on a second. No, my mistake. Acetic acid is closer to 5. It's right in here. So it's going to come up here close in this neighborhood, right up in there. So if you have a smaller K value, the equivalence point is going to be more basic. And if you have a lower K value, the equivalence point is going to come at a lower pH. Okay, so here's a case where we're titrating ammonia with HCl. And notice you start off at a high pH for the ammonia. And then as you add the acid, the pH decreases. until it reaches a somewhat flat region. It's not perfectly flat, but your buffer is exactly 1/2 the volume here of the hydrochloric acid. Equivalence occurs here at this pH, okay, which is acidic. And the buffer is at the pK for ammonia here in the neighborhood of 9. Now let's see, let's go back to ammonia. Let's see. There we go. So the pKa for ammonia is 9.25. Is that right? Yeah, it's 9.25. So that's why we get the, excuse me, here. 9.25 is in this region right here. Right? That's the pKa for ammonia. Ammonium, actually. And we can relate that to our Henderson-Hazelbach equation, where the ammonia and the ammonium ion are in equal amounts. Then the pH is equal to the pKa of that reaction. Okay? All right. So what's an indicator? Well, an indicator for acid-base purposes is usually a weak acid. Doesn't have to be, it could be a weak base that's added in very, very tiny amounts to your solution. And it undergoes an acid-base reaction of its own in parallel with the acid-base reaction that you are conducting in for your experiment. Why would we put an indicator in there? Well, this acid-base reaction for the indicator causes, at a certain point, it causes the indicator to change color. And if it changes color at the same pH where your reaction is at equivalence, then you can use the indicator to tell you when your reaction has reached equivalence, when it's at the stoichiometric point. So, that being said, you have to pick your indicator very carefully so that it changes color when your reaction reaches completion. Here's an example. Phenolphthalein. We use this one all the time in the lab. We know as a qualitative matter that when our solution is acidic, then the solution will be clear, have no color. And when it turns basic, it turns pink. And we use that to indicate the endpoint of a titration. Now, when does that point occur? When does it change those colors? Well, let me see. Well, it needs to change colors when we reach the equivalence point. So if we were to say, the indicator can be treated as a buffer, right? So this expression, actually we can use a Henderson-Hazelbach expression for this, but I don't think it's in the slides. Oh, there it is. Okay, we will use it in a second. So you've got to pick the color change event. When does it occur? Well, notice that we, in this reaction where we have the generic indicator, the reaction is between the acid form of the indicator and the conjugate base form of the indicator. So when we have consumed enough of these hydrogen ions by adding base, then we produce a sufficient amount of the ionized, the conjugate base indicator, to produce that pink color that we can see with our eyes. So there's some physiology going on here too, right? When can we detect that change? Well, the pK for this reaction is 9.4. So that means for this reaction, it's going to be equal amounts of indicator of conjugate base indicator with the acid indicator is going to occur at 9.4. So if we look at it on a titration curve for the indicator, we're going to see a titration curve for that indicator that goes like this. Okay. And for that particular indicator, this occurs at 9.4. At 9.4, you have this ratio is equal to 1. You have equal amounts of these two, right? So when you keep adding base, in our titration, right, we've got another reaction going on at the same time, the reaction of interest. Say we're titrating acetic acid. When does acetic acid reach equivalence, right? We saw that earlier. It reaches equivalence at 8.72. So if we were titrating acetic acid, it would reach equivalence at 8.72 for acetic acid. This pH changes at 9.4. That's where you have equal amounts. So what we want to do is produce enough of this to make the pink color. So we got to move it a little further past there to make enough pink color to detect it. Well, that doesn't look like it's very close to 8.72, 9.4. That's where physiology comes in. Okay. If we're going to detect this color change, we have to recognize that the eye, the human eye, can detect a difference if the ratio of these is 10 to 1. So for the acid side, you're going to have 10 times this amount would be the acid or clear. For this side, if you had 10 times as much of this, this is going to be the base and clear. Okay. So what does that range happen to be? Well, that's where Henderson-Hazelbach comes in. So if we say that the indicator ratio here is 10 times as much conjugate base as acid, that means 10 is in the numerator and 1 is in the denominator. And that would be the pKa plus 1, right? Because 10 to what power equals 1? Excuse me. No, 10 to what power equals 10? 10 divided by 1. So 10 to the first power equals, so it's pKa plus 1 gives you the weighted toward the pink color. And the other way around, 1 divided by 10, pKa minus 1, will give you the pH weighted in the other direction. And then there's a transition in there. Okay, so we got a fairly wide range. And the range happens to be 8.4 to 10.4 because it's 9.4 plus 1, 9.4 minus 1. So this falls within that range. That's why we can use it. Okay, so we can do that with any other type of indicator. And this is it's kind of small print. But notice the pH up here along this line. And if we go over here to that one and we fall down here to phenolphthalein here, then we see that the pH change starts changing in the 8s and goes on up to the 10s. So it's a gradual amount. And some people might be able to detect that pink color a lot earlier than others. So there you have potential for operator error. So the earlier you can detect that pink color, the closer it is for acetic acid to the actual pH at equivalence. Okay, fortunately, we've got these charts, and they give you the color change for each of these indicators at different pHs. Just remember that each one of these indicators is undergoing a buffered reaction at the same time as your main reaction is happening, and they're changing color to help you indicate. So say we use brome cresol green. It changes from yellow to blue. It goes from yellow, green to blue. And that occurs over a range of just under 4 to about 5.5. So if the equivalence point for your reaction that you calculated is in that range, that's the one you use. And you just go to this chart. You have to do some calculations ahead of time and find out at what point is the equivalence occurring, what pH, and then you pick your indicator to give you that. Now, why would we even bother with that? All right, everybody's got a pH meter. You could just do a titration and find exactly when the equivalence is. Yeah, you could do that. But you know how long it takes to do a titration, right? Even a person that's really good and fast at titrating, watching the pH meter and doing the entire curve would take you between maybe 20 to 30 minutes for each one. Whereas if you use an indicator, you can knock out one sample in under a minute. Go to the next sample, minute. So you can do, in a couple of hours, you can do 120 samples. That's why we use indicators, because it's quicker. And the introduced error for this range of color change is minuscule. Why? Because pH is a logarithmic scale and equivalence is a linear scale. Okay, so that's it for chapter 15.